Yeah, thanks a lot. Thanks for inviting me to give this seminar. And yeah, as Anke was mentioning, today I'm going to speak about probing axion-like-particles at Kaon experiments. Actually changes slightly bit my title, including also other light meson experiments, as we'll see. So this is the outline of this seminar. So first I will introduce, so what are the beyond the standard model theories that we would like to probe. So we want to probe, first of all, axion-like particles, in general, any relatively light pseudoscalar. And in particular, we would like to probe its interactions with standard model particles at dimension 5. So we see what are the dimension 5 operators that we can write down for the interactions between axion-like particles and standard model. And then the second part of the talk will be dedicated to experiments and to try to understand what are the light meson experiments that can be useful for us for testing these dimension 5 operators. So I'll focus on two types of experiments. On one side, there are pion experiments. Here I'm listing the two that I will focus on, the PIENU and the PI-beta experiment. And on the other side, there are Kaon experiments, NA62 and KOTO. And these are particularly exciting because they are running now and they will be collecting a lot more data in the future. We see how to use these experiments to probe some specific operator, so some specific interaction of the ALP with the standard model, in particular the interactions of the ALP with with the SU2 gauge bosons of the standard model with gluons. And so all this seminar is based on these two publications that I'm listing here. And before starting, I want to specify that, so whenever we talk about light dark sectors, and in this specific case, light axion-like particles, we have to specify how light, and the focus of this seminar will be on axion-like particles that have a mass in, say, between the MeV range at the few hundred MeV or GeV scale mass. Okay, so that's the goal of this seminar. So let's start with a little introduction about axion-like particles. So why I find them interesting. So first of all, we know that axion-like particles, or more specifically the QCD axion, has been proposed to address the strong CP problem. So to understand why this operator that I can write down here is so much suppressed in such a way to not lead to too large contributions to the electron EDM. We know also that the QCD axion in a specific mass range and for a specific for specific values of the decay constant Fa can be a good dark matter candidate if it is very, very light. In the last few years, there have been quite a bit of activity in proposing new models for axion-like particles that still address the strong QCD problem, the strong CP problem, but with axion-like particles that are heavier and also with a decay constant that is smaller than what is predicted by the QCD axion. And so this gives us extra motivation for considering axion-like particles with masses that are in the MeV range or above, and also with decay constants that are not too large. Beyond the stronger CP problem, we know that axion-like particles, or in general pseudo Nambu-Goldstone bosons with a coming from a spontaneously broken global symmetry, are very much generic in beyond the standard model theories. We know that there are theories that try to address the hierarchy problem, like the relaxation theories that do contain particles like this. SUSY extended models like the NMSSM with an approximate plate-shaping symmetry. We know that axion-like particles can, in principle, address some of the anomalies in data like G-2. And in general, they give us a portal to what we call the dark sector, so to any set of particles that are not charged under our own gauge symmetries and the standard model. So all of these give us a lot of motivations for trying to search and probe light pseudoscalar particles. And of course, the question is how these particles are interacting with us, with the standard model. And so what is the Lagrangian that we can write down? So at dimension 5, we know that axion-like particles can interact with gluons, as we can see here from the first operator, with SU2 gauge bosons, U1 gauge boson of the standard model, as well as fermions with derivative interactions of this type. Now, what is interesting is that the second and third operator that we see written down here will mediate the coupling of the ALP with photons in the broken phase. And this coupling is the main coupling that has been studied from the phenomenological perspective. So in the literature, you can see plenty of pheno studies of how to probe this coupling of the ALP with photons. A little bit less attention has been received by other couplings of the ALP, as for example, the coupling of the ALP with WW, with ZZ, Z gamma, with gluons, as well as fermions. And we should try really our best to phenomenologically probe also these couplings. And in particular, of course, what we expect is that all these couplings will scale like 1 over Fa, where Fa is the decay constant of the ALP. But in general, depending on the UV completion of this theory, these couplings can be quite different. So phenomenologically, we should try to probe all of them independently. And the focus of this talk will be to probe these first two couplings that you see here. And then I will comment a little bit on the other couplings and how they can be probed and what are the phenomenological consequences of those as well. Okay. So that's what I want to do for the rest of the seminar. And of course, I wanted to mention that if you want to interrupt me with questions, just feel free anytime, also during the seminar. So what are the main phenomenological consequences of these two operators? So the first operator, as I already mentioned, will induce the coupling of the ALP with standard model electroweak gauge bosons, and in particular with photons, but not only with photons. Also, as a second consequence, we'll have loop-induced couplings with standard model fermions, as we can see from these penguin-like diagrams. And this includes also flavor-violating couplings. That's why here I put I and J to indicate that in principle we have flavor-violating coupling of the ALP because of this coupling with WW tilde. Okay. If you take the second operator will induce, is an operator that couples the ALP with gluons, as well as we'll discuss more in detail, it will induce the mixing of the ALP with standard model mesons with the right properties, right CP properties, and in particular the mixing of the ALP with a pi0 of the standard model. Now, this mixing is quite important and quite generic if you want. Of course, here I will, discuss this mixing in the context of this operator AGG tilde. We know that the mixing will scale like F pi over Fa and then some combination of masses. But we know that this mixing will be induced also by other operators, as for example, this coupling, this derivative coupling of the ALP with fermions. And in general, this mixing is something that generically happens in theories for axion-like particles. And as I will argue, this mixing between the ALP and the standard model pions is sometimes a quantity that is very interesting phenomenologically. And there are experiments that are probing directly the mixing So it will be interesting to understand what is the bound on this mixing angle. And then, of course, we can reinterpret it back as a bound on the several operators. Okay. So this is a quantity that can be probed directly at some of the experiments that I will mention later during this seminar. Okay. Having said that, so what are the light meson experiments that I will consider? So on one side, as I already mentioned in my introduction, there will be pion experiments. So the pion experiments that I will discuss are trying to probe the rare decays of the charged pions. So as we know in the standard model, the charged pion decays, even if with a very small branch ratio, to a pi0, a positron, and a neutrino. Then, of course, if the pi0 mixes with a ALP, then the pi plus will decay also to a plus, a positron, and a neutrino. And in this decay mode, so the production of the ALP at these pion experiments will depend directly on the ALP-pion mixing angle. Okay. So producing the ALP at these experiments will directly probe the mixing angle that I was discussing at the previous slide. The decay of the ALP will be more model dependent. It will depend on the operator or the Lagrangian for the ALP that I'm considering. So the ALP can decay to photons or to a plus E minus, can be invisible to mu plus mu minus, and so on and so forth. So the specific signature will depend more on the model that I'm considering. So this is for pion experiments. Then for Kaon experiments, the goal, as we see, will be to produce ALPs from Kaon decays, and in particular from K to pi a. There are different production mechanisms of this ALP depending on the operator that I'm considering. If we consider this operator a WW tilde, there will be penguin diagrams. So a D to S transition that is producing an ALP. And instead, if we consider the operator A-GG tilde, there will be mixing effects that are producing the ALP, because we know that in the standard model, the Kaon decays to a pi and a pi0. And then because of the mixing, we can produce the ALP. Okay. So this is from the production side, and then again, from the point of view of the decay of the specific signature, it will depend on the model, and the ALP can decay to plenty of different things as listed here. Okay. So this is generically what what we will search for at our light meson experiments. And before seeing what type of bounds we can have, let me introduce the experimental landscape. So let me introduce briefly how these experiments work and what they search for. So there will be two sections, obviously, one for pion experiments, the other one for Kaon experiments, and then we'll see that we have also proposed some new search for a Kaon experiment, in particular for KOTO. That is the search that I'm listing here that it has been not yet performed. So let's start with pion experiments looking for pi plus rare decays. So first of all, in the standard model, we have this first decay, pi plus going to a positron and a neutrino, that has a very small branch ratio because the branch ratio is elicity suppressed. The most precise measurement has been done at the PIENU experiment at Triumph. So this is an experiment that has already finished collecting data, but they are still analyzing data, in particular in the context of looking for light BSM particles. It's interesting that actually, if you look at the specific numbers, we see that experimentally the branch ratio has been quite well measured. We are speaking about an experimental uncertainty at a level of few per mil. But actually, the theoretical uncertainty is even smaller, so this would justify us to try to improve also the experimental measurement. So this is for the pi plus going to a positron and neutrino. And then there is another decay in the standard model for the pi plus going to pi 0, a positron and neutrino. Obviously, in the standard model, the branch ratio is very, very suppressed because of phase space now. The pi 0 has a mass very close to the pi plus. The most precise measurement has been done by the pi beta experiment at PSI, that is a relatively old experiment. Again, the branch ratio has been measured at the per mil level, so quite accurately, and the uncertainty, the experimental uncertainty is similar to the theory uncertainty. And so in this context, actually, an ALP can produce a very, very similar signature, because if you look at the pi plus decay to an ALP positron and neutrino, if the ALP decays invisibly, then we are in the first category. So we'll have simply a positron and a neutrino to look for. If the ALP decays to 2 photons, then we are in the second category, mimicking the pi 0 positron and the neutrino of the standard model. Okay, so these are the two signatures that we will look for to constrain ALP parametric space. Then from the point of view of Kaon experiments, again, looking for Kaon rare decays. Here we have the charge mode, so the K plus going to a pi plus neutrino antineutrino. We are looking for this decay mode at the NA62 experiment at CERN. Actually, it's pretty exciting because relatively recently, the collaboration announced the first evidence for this very rare decay of the standard model, a 3.5 sigma evidence. In the standard model, as we see here, the branch ratio is super suppressed. We are talking about a branch ratio at the level of 10 to minus 10. And this is the experimental situation that does agree, I mean, the measurement does agree with the standard model, but of course with huge errors. Then there is a neutral decay mode, as we see here in the second part of the slide. Again, the standard model prediction, the branch ratio is very suppressed, and the signature is even more challenging to be looked for. And this is the task of the KOTO experiment in Japan at J Park. And so far, we don't have yet an evidence for this decay mode, and the collaboration observed something like 3 events with 1 expected background event. What is interesting also, there is a relation between the neutral mode and the charge mode via the what we call the Grossman-Neal bound, that is telling us that what we expect not only in the standard model, but in any, beyond the standard model theory with heavy new physics, is that the K-long branch ratio cannot be much larger than the K plus branch ratio, and so there is this bound. Okay. And then again, what about ALPs? So ALPs can mimic these signatures because if you look for the K plus going to pi plus and then ALP, with the ALP decaying invisibly, we are mimicking the first signature. And then similarly, if you have a K long going to a pi 0 and then ALP with an invisible ALP, we mimic the second signature. Going in parallel with pion experiments, we might ask, what about having an ALP decaying to photons? And this signature, of course, is different than the signature that NA62 and KOTO are looking for to measure the standard model. The signature has been looked for in the charge mode by past experiments that I'm listing here. So this NA49 and E949 and NA6248 experiments were looking for a K plus going to pi plus gamma gamma. Not necessarily, thinking about axion-like-particles, but data can be reinterpreted in terms of bounds on axion-like-particles decaying to photons. And the NA62 experiment didn't yet perform this specific search for an ALP. But we can, what we have done in our paper is actually to rescale the bound, so the analysis of NA6248 in terms of using the full future luminosity of NA62, and we see what is the result. For the neutral mode, what we have done is actually to propose a search for the KOTO experiment. There is not really much in the literature for gamma signature of this type. And the reason is that actually a signature like this is pretty challenging to be looked for at experiments, at Kaon experiments. In particular, KOTO, if we go into the details of the experiments, you will see that KOTO only has a calorimeter to look for photons. It doesn't have any tracker. So you cannot really directly see from where the photons are coming from. And having 4 photons, there can be problems of pairing because you don't know what are the photons coming from the ALP and the photons coming from the pi 0. So what we have done is to try to, we have done a collider analysis to see what are the prospects to look for these signatures, the signature at KOTO, and trying to pair in a correct manner the photons. Basically, what we have done is a Monte Carlo that tries to see what are the photons that are reconstructing the pion mass. The other 2 photons will reconstruct the ALP mass, and then we reconstruct the full invariant mass of the K long coming from these 4 photons. Of course, it's pretty tricky. We have to require, so the experiment needs to have a very good vertex resolution and good energy smearing. Otherwise, a signature like this is nearly impossible to be seen. And in our analysis, we also simulated the main background sources coming from pi 0, and pi 0 gamma gamma, resonant pi 0 gamma gamma. And putting everything together, we saw that actually a branching ratio K long going to pi 0 and then ALP at a level of 10 to the minus 9 in the most optimistic regional parametry space can be probed using the full luminosity, the full future luminosity of KOTO. Of course, if you are too close to the pi 0 mass, so if you see here on the x-axis, I'm showing the ALP mass. And if the ALP mass is very close to the pion mass, then the background coming from pi 0 is quite larger. That's why you see here the prospects are not as good as beyond the pion mass. Okay, so this is just a little some exercise that we have done for the KOTO collaboration, and actually now the experimentalists are actively looking for this signature. So this is a work in progress. And now we'd like to understand indeed how all this experimental information can be used to set bounds on ALP couplings to standard model. So this is the second part of this talk. So we'll try to understand how these pion and Kaon experiments can set bounds on these 2 operators. So on one side, AW tilde, on the other side, GG tilde. Okay, and in particular, we would like to understand if indeed the scale that is probed by these experiments is an interesting scale from the EFT perspective, or if it is a too low scale from the EFT perspective. Yeah, I don't know if there are any questions already. Let me pause a little bit.
Hi, I have a question.
Sure, yeah.
So which lifetimes are you covering in the past plot in the KOTO experiment?
Oh, great. Thank you. I didn't mention that. So here, actually, we are only considering prompt ALPs. And the reason being that if the ALP is long-lived, this search is super challenging. And the reason is that, so I'm using the information that the ALP is prompt here, namely that you see from this cartoon, you see that the 4 photons are coming from the same point. And then having this assumption, of course, I mean, with experimental uncertainties, but having this assumption allow us to reconstruct the full event. So you have basically kinematical information from invariant mass and so on that tell us that we can reconstruct the full event. If the ALP is decaying afterwards, it's very complicated because you don't have a tracker in this experiment. So the analysis that we have done is only for ALPs that are short-lived, so they're prompt in within, say, a centimeter or so. That is the experimental resolution.
Okay, thank you.
Can I also ask a question, Stefania?
Of course, yeah.
You probably mentioned it, but I wasn't there from the very beginning. So why are you only looking at those two benchmark models with the coupling to SU2 or Kaon? Because I mean, if you want to generate flavor violation from the ALP, it's of course much more efficient to couple to quarks.
Yeah, absolutely.
Right? I mean, one wins by more than 2 orders of magnitude if you have a coupling to the top quark. So basically, is that just for simplicity, basically? Because I know that many people look at the W coupling to generate flavor, but it's really the most inefficient way. Yeah, it's actually, even the gluon coupling actually generates bigger flavor violation than the W through two-loop evolution effects.
Yeah, absolutely. So I fully agree with what you say. So having so starting with that operator, let's go back. So starting with this coupling of the ALP with tops, you will generate flavor violating couplings. So you will have those effects. I mean, those Kaon decays that we will talk about, yeah, it's a matter that we started from somewhere, basically. Okay. But absolutely, I mean, it would be interesting to see how all the experimental bounds that I will discuss in the second part of the talk can be interpreted in terms of the coupling of the ALP with fermions. And then, as you say, yeah, as you pointed out in your papers, actually, also the gluon coupling will generate flavor violating ALP quark interactions that should be also studied. So when we'll discuss the A coupling with GG tilde, the analysis that we have done is in the Carrel Lagrangian, where we consider only mixing effects, as we see. But actually, I would like. So I was reading your papers, and I would like to understand. This was not even
the point I worried about. Now, I really thought that instead of the WW, one should probably also look at the last term here, simply because.
Absolutely, yes. Yeah, it should be done. Yeah, absolutely.
Okay.
Right. Any other question? Okay. So let's start with this second part of the seminar, and in particular, let's start with this AWW tilde interaction. So as we already mentioned, this interaction will lead to this flavor violating couplings. And in particular, I'm interested to the S to D transition that is mediating my Kaon decay to a pion. So the effective coupling, so the coupling of the ALP with the down quark and then the strange quark is written down here. Of course, we'll have proportionality with this GAW coupling in blue, as well as to CKM elements. Then we can compute the rate for K long to a pi 0 and an ALP, or of the rate of a K plus to a pi plus and an ALP. So the first rate will depend on the imaginary part of this coupling, this effective coupling, and the second rate will depend on the absolute value of this coupling. And because of this dependence, as actually already expected from the Grossman bound, we expect that the two decay modes are related. And in particular, we expect that the second width, so the width for the charge mode will be larger than the width for the K long for the neutral mode. And so we can compute the branch ratios. So here in this plane, I'm showing so the dashed lines are are for the branch ratio of K long to a pi 0 and an ALP. the branch ratio for the K plus is always related in this case to the branch ratio for the K long. In particular, there is a ratio of 1.8. And also in this plane, what I'm showing is are the regions of parameter space in which the ALP decays either promptly or invisibly. Promptly, if the lifetime is very, very short. For having an invisible ALP, it depends on the experiment, of course. So for KOTO, it's pretty easy to be invisible in the sense that KOTO, as shown in this cartoon, has a detector that is relatively small, of a few meters. So if the ALP has a lifetime that is longer than a few meters, then it will look like an invisible ALP from the KOTO perspective. For NA62, we have to require a longer lifetime because NA62 is a much larger experiment as shown here. So we have to go to coupling constants that are smaller. Okay. So what are the regions of parameter space that have already been probed by past experiments? So here you see all the regions in gray are the regions already probed. So what are all those regions? So the region at low values of this coupling constant is the region probed by past beam dump experiments, and in particular by the CHARM experiment, that is a past proton beam dump experiment, where basically the ALP could be produced via the Primakov effect, thanks to its coupling with a photon. And we see that the type of scales that have been probed, if you think about this coupling scaling like 1/FA, are 100 or thousands of TeV, roughly speaking. Then we see in blue, so this region 4 is the region probed by this past NA6248 experiment looking for K plus going to pi plus gamma gamma. And then finally, these regions 2 and 3 are regions probed by past colliders, and in particular by the CDF analysis, the search for a Z boson going to gamma gamma in quotation mark, because here the idea was to look for a Z boson going to a photon and an ALP, and then the ALP going to 2 photons, but these 2 photons coming from the ALP were pretty much collimated, so that we were looking simply for a 2 photon type of signature. And then finally, we have the LAP experiment looking either for the production, looking for a production of a photon and the ALP, and then again with the ALP going to gamma gamma. Okay. So this is just to give you a brief overview of past experiments and the regional parameter space probed. Of course, I mean, the region on top of this plot is a region in which the ALP is decaying promptly to photons, and the region down there is the region in which the ALP is long-lived. That's why it could have been seen at beam dump experiments. Now, what can we do at the present and future Kaon experiments? So here I'm shading the regions that could be probed in the future, either by NA62 or by KOTO. So let's focus on low coupling constants. So at low coupling constants, you can see this KOTO 2 gamma and NA62 0 gamma. And this, the idea is to look for K plus going, Kaon going to a pion and an ALP with an invisible ALP. And what we have done to draw these regions is to reinterpret data of KOTO and NA62 and then projecting it with a full luminosity. What we can see is that there are sort of extra regions of parameter space that can be probed, even though it's kind of challenging to beat the old beam dumps. Still, there are additional regions that can be probed. Now, if you look at signatures with more than 2 photons, so 4 photons at KOTO or 2 gamma at NA62, where the idea is to look for an ALP decaying to 2 photons, then we see that we have plenty of regions of parameter space that can be probed. In particular, you can see here the red region, so everything above this line can be probed by this proposed search for KOTO that we discussed a few slides ago. And what is interesting is that actually you see that you can basically close entirely the region below, say, 150 MeV or so, putting together, you know, a 4 gamma signature and 2 gamma signature, where indeed the ALP is either invisible or decays to 2 photons. Okay. So that's pretty interesting, and we are looking forward to the, you know, to the real analysis by the KOTO and the NA62 collaborations. So this is for the prospects for probing the ALP-WW coupling. And then let's see what we can do for the ALP-GG tilde coupling. So for this coupling, what is useful to do is to do a chiral rotation in such a way that of the quarks of the standard model in such a way that we get rid of this coupling in favor of the coupling of the ALP with quarks. And then we can match onto the chiral Lagrangian. What we can see is that we'll generate 2 operators. So the first operator will mediate a kinetic mixing of the ALP with the mesons of the standard model. So this sigma, as we see here from this slide, contains all the light mesons of the standard model. So actually not only the pi 0, but also etas and also Kaons, of course. And then we have the second operator that will mediate a mass mixing between the ALP and the mesons of the standard model. Because you see here, this mass matrix M in red does contain the ALP. Okay. So if you do this exercise in this particular basis, what you will see is that you generate a kinetic mixing between the ALP and the pion that has this form. As we were already mentioning before, we expect to have a scaling that goes like F pi over Fa, some combination of masses, and then some combination of quark masses as well that are contained in this kappa U and kappa D. We also do generate a mixing between the ALP and the eta of the standard model. And this mixing has a more complicated form because to compute this mixing, you have also to keep into account the fact that the eta of the standard model mixes with eta prime of the standard model. And this will lead to both a kinetic mixing and mass mixing between the eta and the ALP of and the ALP that I'm considering. Okay. So these are the 2 mixing terms that we computed. For phenomenological studies, the first mixing term, so the ALP mixing with the pion, is the main mixing that has been considered. And then we'll comment on the role of the second mixing. So let's not forget about the mixing between the ALP and the eta of the standard model. So let's first focus on the ALP pion mixing. So if we have this mixing as produced from this ALP-GG tilde operator, then as we already argued, we'll produce the pion decay to an ALP, a positron and a neutrino. So to compute this decay mode, what we have done first is to compute the matrix element that will scale obviously with the sign of this mixing angle times the matrix element of an off-shell pi 0 and the pi plus. Or the additional contributions will be quite suppressed. And so the matrix element for a off-shell pi 0 and the pi plus will depend on 2 form factors. And actually only this F plus form factor is the relevant one. We know that is approximately equal to 1 if the Q square of the process is relatively small, that tell us that we need to focus on ALPs that are relatively, not too light, say above 10 MeV or a few MeV. And then having this information, then we can compute a few branch ratio as well as the kinematic of the process. And actually, the kinematic of the process is very important if then we want to reinterpret the pion experiment data. And so let's start to see how to reinterpret the PIENU data. So what PIENU is doing is to produce a beam of pi plus that is then stopped in some target. So we'll have a pi plus decaying at rest. And then PIENU is looking for measuring the positron coming out from the pi plus. And PIENU is giving us information about the energy deposited in the calorimeter that is shown here in this cartoon. And of course, if you have the pi plus decay to an ALP, a positron and neutrino, the energy deposited in the calorimeter will be different than the energy deposited from the standard model decay. So we have done some Monte Carlo simulation to understand what is the energy deposited in the calorimeter, depending on the ALP mass. So the first regime that we studied is an invisible regime in which the ALP is just escaping. These two curves correspond to different masses of the ALP, either 80 MeV or 40 MeV. And you see how the energy deposited by the positron changes, depending on the mass. The second situation is the situation in which the ALP decays to photons promptly. Because of the mixing of the ALP with the pion, we know that the ALP will also decay to photons. And then, of course, if it decays to photons, the energy deposited in the calorimeter will be different because it is energy coming both from the positron and from photons eventually. And then, therefore, also this distribution will change as we see from these curves. Okay. We can compare with data. Actually, you see in this plot, I'm reporting the data. So these are residuals that the PIENU is giving us. And if you do so, as we see, you can extract a bound, and we see the bound in a couple of slides. So this is what you can do to reinterpret the PIENU analysis for the standard model pi plus to E plus neutrino decay. What about pi beta? As we were mentioning at the beginning of the seminar, pi beta is looking for a pi plus going to pi zero, positron and neutrino. And again, if you have the pi plus going to a ALP, positron and neutrino, with the ALP going to gamma gamma, you will have some contribution to the data of pi beta. Of course, the difference here will be that the photons, the angular distribution will be different. Because we expect that the photons coming from the pi zero, the standard model will be basically back to back because the pi zero and the pi plus have a similar mass, and then the pi plus is decaying at rest. The ALP will have a generic mass, so in general, the photons will have a different angular distribution, and they will in general have smaller opening angles. And then again, we have done a Monte Carlo simulation for this experiment, and then we have seen what is the angular distribution of these photons and compared with data. Unfortunately, we have only information for a very small range of angles, namely for a photon opening angle between 160 degrees and 180 degrees, because this pi beta was simply looking for standard model decay. So we were only interested to very large opening angles. And this is also a old experiment, so we cannot really gather much more information than this. But already using this amount of data, what we can see is that we can extract this interesting bound on the mixing angle. So you see that pi beta can only set bounds for ALP masses that are not too light, because otherwise the opening angle becomes too small and we don't have information. And then we see also the bound coming from PIENU. And we see that mixing angles at a level of 10 to minus 3 or so can be probed generically. Of course, you can interpret this bound on the mixing angle in terms of our AGG tilde operator. We see that actually the scale probed here is very, very low. It's not that large. But then you can do the exercise, and as I mentioned, I mean, you can interpret this bound on the mixing angle in terms of other operators, and then the bound can be more stringent if you interpret it in terms of coupling with fermions or any other combination of operators. And what I want to stress here is that these experiments, so the bound is a bound that is directly on the mixing angle, and then you can reinterpret back in terms of operators. Okay. So this is what we learned from the perspective of pion experiments. Let's see what we can do at Kaon experiments. So Kaon experiments, again, we look for K to pi A, and then the A will decay to photons because of the mixing, the induced mixing of the ALP with pion and eta. So let's see what is the rate for K going to pi and then ALP. Again, what we can do is to match onto the Carrel Lagrangian, and in particular, there are two different operators that will mediate an S2D transition. The two operators will have in front Wilson coefficients that are actually measured, because these are, will mediate K to pi or K to eta transitions in the standard model. So these G8 and G27 coefficients are measured. And then these operators, once that we introduce the ALP mixing with a pion and the eta of the standard model, these operators will also lead to a K to pi A transition. Okay. And what is interesting is that actually we can compute the rate, and the rate, so let me show you the plots for the branch ratio of the charge mode or the neutral mode. So let's focus on the charge mode for a second. In this plot, you can see three curves. So the curve in black is actually the full result that keeps into account both of these operators that you see in this slide, as well as the mixing that is with the induced from the AGG tilde operator, the mixing with the pion, as well as with the eta. Okay. If you forget about the mixing with the eta, as it has been done generically in the literature before, you see that you would get this blue curve that is obtained only considering the ALP mixing with the pion. And you see that the result on the branch ratio will be quite different. And the reason is that actually there are cancellations that are arising. That's why you see that this black curve is dipping at particular values of the mass. So this gives us indication that we really need to consider also the mixing with the eta of the standard model to have a more correct calculation of this rate. Okay.
So Stefania,
yeah.
Do you mean the eta or the eta prime here?
Eta.
Oh, really the eta. So you're just talking without the eta would just be pi zero mixing.
Correct.
Okay. Thank you.
Yeah.
Thanks.
That's right.
Sorry for interrupting.
Sure. No, actually, yeah, thanks for the question. And actually, so to compute this mixing with eta, you have to consider also the eta prime mixing in the standard model. So it's an interesting calculation. So the eta prime is also playing a role in this calculation. But here we are introducing the ALP mixing with eta. And actually we are working now on trying to understand what is the role of the mixing with eta prime as well, because here in this calculation we consider the eta prime as decoupled. Okay. But yeah, we can discuss more details later on also if you like. Yeah. So what about the neutral decay mode? So for the neutral decay mode, the role of the ALP beta mixing is not as important. Actually, there is only one operator that is mainly contributing. I think it's this G8 operator. And as you can see, considering only the mixing with a pion wouldn't lead to large errors in this context, because in this mass range, actually, there are no cancellations, and there is one contribution that is the dominant one. So this is just to comment a little bit on this interesting calculation in the context of the chiral Lagrangian. And then we can put numbers, see what are the branch ratios and lifetime of the ALP. And this is what we see in this relatively busy plot. What to take home from this plot. So the take home message is that generically we expect to have the K plus branch ratio to be larger than the K long. But of course, there are these regions of parameter space in which you have cancellations of the K plus branch ratio, as we see here from this previous slide, in which the K long branch ratio can be quite larger than the K plus. Also, we'll have two regimes, the invisible regime or in which the ALP is too long-lived to be seen decaying by the KOTO or NA62 experiment. And then there is the prompt regime at decay constants that are not too large. Okay. So let's see what are the past experiments reach on the parameter space of this ALP-GG tilde operator. So the regions in gray are the regions already probed. Let's see what they are. So at large decay constants, as we would expect, these are the regional parameter space probed by beam dump experiments. There is a combination of proton beam dump and electron beam dumps here. At low values of the ALP mass, as you can see here, the region 2 is coming from the past Kaon experiment, E949. Region 3 is actually coming from the pi beta experiment, so the pion experiment we were discussing before. And we see that, as I argued, the experiment is setting a bound on the mixing angle between the ALP and the pion. You can interpret that in terms of the bound on the ALP-GG tilde operator, but then you see here that the scale probed is relatively small, a few tenths of GeV. Then there is the LAP experiment and the NA6248 experiment that we already discussed that are probing larger masses and still relatively low coupling constant. Relatively low decay constant, the F8. So what we can do in the future, so these are the regions that can be probed in the future via the proposed search for KOTO, so this K long to 4 photons, so the K long going to pi0 and then ALP, and the ALP decaying to 2 photons. And this is the region shown in red. And then we see the purple region is coming from the future prospects for NA62 to look for K plus to pi plus and then ALP with an ALP decaying to 2 photons. Okay. So you see that I'm putting some band, and if you're curious about that, so this is the band that shows the theory uncertainty. Actually, it's very interesting to see that, these calculations have a really large uncertainty, especially because there are these cancellation regions. So if you change just a little bit the quark masses, as we are doing for, determining this band, you see that the reach will change quite a bit, especially for NA62, because the K plus branch ratio can be really affected by this small shift in quark masses because of these cancellations that we were discussing. Okay. Okay, excellent. And then we see that indeed the future prospects that collecting using the full luminosity of KOTO and NA62 will give us good prospects for really improving on this regional parameter space that is tested. And yeah, I will be curious to see if KOTO and NA62 could eventually almost cover the gap between, you know, the past experiment looking for prompt ALPs, so for low decay constant and the beam dumps. Of course, this region in between is always the most challenging region to be looked for, but it would be interesting to see how much we can fill out this intermediate region, as we see here in this plot. Okay. Okay, excellent. So this leads to my conclusions. So I hope I convinced you in this talk that these are really interesting times for flavor physics experiments. There are several experiments that are ramping up, and in this talk I focus on Kaon experiments. Pion experiments are interesting as well, but there are not much experimental prospects of collecting more data, as far as I know. Kaon experiments, we know that we'll have a lot more data in the future. And we have seen that there are good prospects for testing additional regions of parameter space of axion-like-particles at these Pion and Kaon experiments. And there are interesting, you know, theory calculations that we can do for our experimental colleagues, and also new signatures that we can propose that will contribute in probing additional parameter space of these ALP effective couplings.